Well, from the last example, we saw that limit can be used to show inequalities. Of course, this is to use comparison theorem. Now we can state this in a more useful way. Okay, this is the so-called limit comparison theorem. Or just, let me say, test. Okay, here we have two sequences, and they will be positive, and because we will be dividing, we need Bn to be strictly positive, but again, ultimately. Then, if limit an over Bn is L, and L is a finite non-zero number, a positive, strictly positive number, then the series An and Bn converge or diverge together. Okay, this is quite useful in the sense that given an An series, if you can find a suitable Bn, but which is simpler, and if you have such a limit, then you know you don't have to worry about divergence or convergence. It all depends on what Bn's do. Okay. The other cases can also be stated, but they are less useful in practice. If limit An over Bn is 0, then this means, of course, that if you take epsilon 1, it says that An over Bn is less than or equal to 1. When, after some n 0. So then, ultimately, okay, An is smaller than Bn. And use comparison theorem. You have your inequalities. And finally, if the limit of An over Bn is infinity, then ultimately again, you have this time An's are bigger than Bn's. So, and of course, again, use comparison theorem. Okay. I will not concentrate on B and C. They follow directly from the limit definitions. Okay. But A needs a proof, so I will comment on it. Well, L is a positive number. AN over BN has the limit L. So, okay, let epsilon be L over 2. It's a positive number because L is positive. Then there exists an N0 such that AN over BN minus L is less than epsilon if n is greater than this N0. Now we can choose this N0 slightly larger so that actually the ultimate inequality holds, positivity holds as well. Okay, let me add it here. This is true, of course, so choosing N0 larger, we can guarantee that AN is positive and BN is strictly positive. But then, what does that tell us? It tells us that AN over BN is bounded by L plus L over 2 and is greater than L minus L over 2. Okay. Because the inequality precisely says this. Actually, you have strict inequalities. That is not the point. Well, so, okay, this says that Bn is less than, this is by 1, 2 over L AN, and of course it is positive. And by 2 we have AN 3 over less than or equal to 3 over 2L times Bn. Now, this says that up to a constant, which is a positive number, okay, ANs are bigger than BNs, and BNs are bigger than ANs. So if we use comparison theorem here, it says that if ANs converge in the series, so does the series of Bn. If the series of Bn converges, so does the series of AN. So using comparison theorem directly here, okay, let me say theorem to conclude that sum AN and sum Bn converge, diverge together. Okay. Well, as in the case of applications of comparison theorem, still we have to find a Bn given an AN. So with what to compare, is still not clear, but at least we don't have to show inequalities in this theorem. We only have to take a limit, AN over Bn. And therefore, it's a simplification in that sense. Okay. Well, let us see some examples here. Well, the first example is what about sine 1 over n? Well, the task is always to find a good, simpler series whose convergence or divergence we know, and to compare it with sine 1 over n. Now here, okay, we recall that limit x going to 0, sine x over x is 1. So, okay, x going to 0, of course, is equivalent in the sequence form that n goes to infinity. So as n goes to, let me say, so if n is large, okay, sine 1 over n behaves itself like 1 over, because the ratio goes to 1 in the limit. So we guess that the series sine 1 over n is divergent. Why? After comparison with, rather, limit comparison, with 1 over n. Okay, let us do it. The limit of sine 1 over n over 1 over n, of course, both terms are strictly positive for every n, because, okay, sine 1 is positive, and 1 over n is between 0 and 1, and in that interval, the sine function is positive. Well, this is 1, because limit x going to infinity, sine 1 over x divided by 1 over x. So the sequence comes from a continuous function, and so we get that limit. And of course, the harmonic series 1 over n is known to be divergent. So by limit comparison test, the series sine 1 over n is also divergent. Okay. Well, the other example shows, even in a better way, the use of the limit comparison theorem. Okay. Consider the series, say 2 to the n, 3 to the n, 1 plus 4 to the n. Now this is a little bit more complicated looking series, but it's very easy to check that. This term is always strictly positive. So we can try to use a limit comparison theorem type of theorem. Well, the question of with what to compare it, okay, gives us, after some, gives us a hint actually, if we look at an. So the question is, with what to compare it? In all comparison theory tests, we have this question all the time. Okay. So to get an insight, okay, let us see what happens if n is large. Okay. We look at Rn. Now, to see what happens if n is large, okay, we have to take the largest terms out. That would be 3 to the n, 2 over 3 to the n plus 1, over 4 to the n, 1 over 4 to the n plus 1. Clearly, at the top, 3 to the n is the fastest increasing term. At the bottom, 4 to the n is the larger term. Now, if n is very large, 2 over 3 to the n, because the limit is 0, it would be very small. Similarly, 1 over 4 to the n would be very small. In other words, this would look like 3 to the n divided by 4 to the n, 0 plus 1 over 0 plus 1. Okay. So for large n values, this ratio is quite near to an. Now, this gives us two hints. The first hint is that because a geometric series with this general term would be convergent, 3 over 4 is less than 1, we guess that our series is convergent. That's a guess. Secondly, it tells us to compare an with this one. So both ways, we have some hint right now. So we look at limit, okay, an divided by 3 over 4 to the n. Okay. This is, as we already calculated, okay, 2/3 to the nth divided by 1 over 4 to the n plus 1. The remaining terms, that is 3 over 4 to the n, is cancelled with the other 3 over 4 to the n. So the limit is 1. Okay, this tells us that our guess was correct, and the series 3 over 4 to the n is convergent, geometric series. Namely, 3 over 4 is positive, and it's less than 1. So, by limit comparison test, also the given series is converged. Okay. Now, when we look back to our solution, okay, this part is not part of the formal solution. It is how we reach the solution. Okay? It gives us a hint. So this is the guessing part. It helps us, but it's not part of the proof. The proof starts here. Okay. As a third example, let us consider the series pi over 2 minus arc tangent n. Now, the first thing we observe about this series, of course, is the following. Firstly, Okay? If you recall the graph of arc tangent x, it looks like this. So pi over 2 is always bigger than arctangent n. And thus, okay, the general term is always positive for any positive n. Okay. So we can try to use comparison. Well, we have another hint here. The limit of an is 0, because we see it clearly from the graph that the arctangent x approaches pi over 2 when x goes to infinity. So it's still the same with n. Okay, so the series, okay, could be convergent or divergent. This tells us nothing. Or, in other words, the nth term test fails. So the question is, okay, what does this an look like? It goes to 0, yes. But if it looks like 1 over n, if n is large, okay, then the series should be divergent. If it looks like 1 over n squared, the series could be convergent. So which one is that? Okay, since we don't know, okay, we try, okay, a nice enough known series, that means P series, and compare it limit-wise with this an. We try, that's just a trial, and consider the limit of pi over 2 minus arctangent n divided by 1 over n. Okay. If not, we will try 1 over n squared. Okay. If not, then try another. Okay, something like 1 over n squared, etc. Well, here, of course, we have limit x going to infinity, pi over 2 minus arctangent x over 1 over x. Okay, because now x is a real variable, we have a 0 over 0 case. This is a L'Hopital's problem, and so we can calculate the derivatives. So we have 1 over 1 plus x squared divided by minus 1 over x squared. We look at this limit, when x goes to infinity is obviously 1. So we have equality here by L'Hopital's rule. And so, okay, when we go back, we see that this limit is 1. Okay. Now, because we reached a limit value which is not 0 and which is not infinity, a finite positive number, the two series behave similarly. Okay. Now, since the series is divergent, because p is 1, okay, by limit comparison theorem, also the series diverges. Okay. So note that here it's not very clear with what to compare. Okay? And therefore, we tried something, and because the limit is 1, we were lucky. It worked. Okay. Let us consider a fourth example. Okay, 1 minus the exponential of minus 1 over n squared. Now, we likewise see that this limit is 0. Sorry, it goes to 0. Why? If n goes to infinity, okay, this exponential approaches e to the 0, which is 1. So the limit value is 0. So anything can happen. It can be convergent or divergent. Now, we cannot easily see with what to compare. So, again, as in the previous case, of course, it's easy to observe that this is a positive value all the time, okay? Because 1 over exponential of a positive number is always less than 1, and so on. So, as in the previous case, we consider, again by trial, okay, the limit of 1 minus e to the minus 1 over n squared divided by 1 over n. Okay. Now, the limit x going to infinity, 1 minus e to the minus 1 over x squared divided by 1 over x, which is clearly 0 over 0 form, is a L'Hopital's problem. And we evaluate the derivatives. So this would give us minus e to the minus 1 over x squared times 2 over x cubed divided by the derivative minus 1 over x squared. And the limit when x approaches infinity, okay, exists because this term goes to, okay, you can, okay, cancel the minus ones, so it goes to minus 1. And the other part, because you have an x at the bottom, an extra x, gives this to be 0. So indeed, by L'Hopital's rule, this limit is 0 because of this. Now, what does this tell us? Now, by comparison theorem, by rather limit comparison theorem, this says that we have a positive value and it is smaller than 1 over n. Okay. If n is large. Okay. Now, 1 over n has a series which is divergent. Anything smaller than can be divergent as well, or maybe it is convergent. So, okay, since this is divergent, okay, then, okay, the comparison theorem with these inequalities says nothing. Remember, in the comparison theorem, if the larger one were convergent, then the smaller one would be convergent. But if the larger one is divergent, you cannot say anything. Well, so we were not that lucky here. So our approach failed. Since our trial, okay, to compare with 1 over n failed, okay, try, say, something convergent this time. That means, okay, we look at the limit of 1 minus e to the minus 1 over n squared divided by 1 over n squared. Now, as in the previous case, the limit x going to infinity of 1 minus e to the minus 1 over x squared divided by 1 over x squared is still of the form 0 over 0. Okay. Differentiation of the top and the bottom tells us that we have minus e to the minus 1 over x squared, 2 over x cubed, divided by minus 2 over x cubed, which happens to be the limit x approaching infinity of e to the minus 1 over x squared, which is 1. Now, 1 is good, because it tells us, okay, that both series here converge or diverge together. So, by L'Hopital's rule, this is 1, and so this is 1. And we know 1 over n squared is convergent. So the given series is convergent by limit comparison here. So to find the correct thing to compare with is not always, okay, obvious. In that case, we can try a few things. Sometimes we reach the right one immediately, sometimes not. Okay, later when we discuss the Taylor series, etc., a little bit later in this course, we will see how to make a good guess directly. Okay. Our next test, or rather tests, will be quite practical tests. But again, care must be taken.